Hi, in this video I'll give you a quick overview of one of the most useful tools in particle physics, the Feynman diagram. When you first see a Feynman diagram, it may well look incomprehensible. However, once you know a few simple rules, you'll be able to interpret them. Feynman diagrams can be used to represent interactions between particles. The x and y axes of the diagrams broadly represent space and time respectively, but you may also see diagrams where these are reversed. There's no standard way of doing it. Feynman diagrams consist of lines and vertices. Each line, which may be straight or wiggly, represents a particle. Each vertex represents an interaction between particles. There are three very important rules for Feynman diagrams. Every vertex must have one straight line with an arrow going in, one straight line with an arrow coming out, and one wiggly line. Rule 2. All lines must be connected to at least one vertex. A line cannot be on its own. And rule 3. Charge must be conserved at each vertex. Charge in equals charge out. So what do the arrows mean? Well, the arrows represent the direction of movement for a particle. Let's take a look at an example. To interpret this, let's consider each vertex individually. In this example, time is on the y-axis and space is on the x-axis. Beginning with the vertex on the left, we can see that an electron comes in, it releases a photon, and then the electron moves away in the opposite direction, so moving backwards in space. That photon then goes on to have an interaction with another electron, which was travelling in the opposite direction, absorbing the photon and causing that electron to also change direction. Overall, what has happened is that two electrons have repelled each other via the electromagnetic force. Let's check conservation of charge at every vertex. At vertex 1, a charge of -1 goes in with the electron, and a charge of -1 comes out with the electron. The photon has got no charge, so charge is conserved at the vertex. At vertex 2, an electron and a photon go in, total charge -1, and an electron comes out, total charge -1, so charge is conserved. Here's a different example. Again, let's consider it one vertex at a time. At the first vertex, we have a neutron decaying into a proton and an as yet unidentified boson. The boson then continues for a short time before decaying into two more particles, an electron and an antineutrino. But look, notice the neutrino appears to be moving backwards in time. It's moving down the time axis. Don't worry, this is another rule of Feynman diagrams. Antimatter particles will always travel in the opposite direction. They will always appear to be travelling backwards in time. That's just how they get represented on our diagrams. Let's use the idea of conservation of charge to work out what boson provided this interaction. At the first vertex, a neutron comes in with 0 charge, and a proton with a positive charge comes out. In order to conserve charge, this means we must have a boson with a negative charge. The only boson we know with a negative charge is a W- boson. We can double check this at the second vertex. At the second vertex coming in, we have the W- boson with a charge of -1. We also have the antineutrino coming into the vertex because the arrow has been drawn against the direction of time due to it being an antiparticle. Note that this particle isn't actually moving backwards in time, it's just how we represent it. So we can add the 0 charge of the anti-electron neutrino, and coming out of vertex 2 we have only an electron with a -1 charge. So charge is conserved. Thank you for watching this video from Cowen Physics. If you found it useful, please like, subscribe, and visit cowenphysics.com.